We'll go through some example problems for material indices because this question is definitely coming here. So let's open up some example problems over there. Should be here. No, design of mechanical. Okay. The lectures, chapter 2. Okay. Where have I put it? It's not here. Okay, so it should be V1. Apparently the word file is missing. Okay. Okay, so what are some of the examples I have given? And this is given, I think I have posted this also online. Now, what we are going to discuss is how to derive for simple cases, how to derive the material indices. And from the material index, how do we draw or how do we draw the guidelines in the Ashby chart? Okay, so that is the requirement here for for explaining the problems. Let's just go to the notepad here. Before I do that, I also need to connect my iPad because I cannot write it without it. Just hold on a second. Okay. Hopefully this works. Okay. All right. So let's go to this specific example here. We're asked to design a light, stiff beam. Okay. Let's take this simple example. Design light, stiff beam. That means first, what is the objective function? We list that. What is the objective function? Minimize mass, which can be written as rho times volume, which can again be written as rho times area times length. So this is the first step. The second step is identify free variables. Okay, in the case of a beam, usually the span or the length of the beam is fixed. Okay, L is fixed. So rather I should write here fixed variables. Let's first identify fixed variables. So naturally other variables will be free. Okay, so length is fixed. What else is fixed? Perhaps the shape will be fixed, or maybe shape is also a free variable, but let's make it simple and say the shape of cross section is fixed. So besides that, maybe boundary conditions are fixed, maybe a cantilever beam, whatever it is. Okay, so in this case, let's assume this is a cantilever. Okay, and then what else? So these are the fixed variables. So obviously the free variables are then whatever is left. What are the free variables? We can have area of cross section, the material property rho, E, etc. Here, since we want a light stiff beam, that means rho must be a free variable. Material choice is free, and therefore rho and E both should be free. Area of cross section is free. Okay. So after identifying these variables, then we have to come up with some relationship. Usually we need some kind of relationship to work the problems. What is the relationship? Since we want a stiff beam, this means, so let's write here, so E is fixed. Okay, so that should be okay. What is the relationship we want? We want the deflection Y for the beam. So usually this deflection may be provided, and this is of the form here. Let's see, EI over okay, so I don't think they have provided this explicitly here. So the deflection will be, I think, some constant times maybe EI over L cube over a length L. So this is of this form. It is of this form, basically. See, this is the stiffness. What they have provided here is the form of the stiffness rather. So let's write here. This is equal to your stiffness K. Stiffness is nothing but force over Y, the deflection Y or delta. Okay, so let's write it to make it very clear. Delta. So from here we can see FL cube over C times EI will be your deflection, end deflection for a cantilever beam. You are directly given this relationship. Now this stiffness is supposed to be less than some given stiffness value, because you want a stiff beam. How stiff the beam should be, that should be mentioned, and sorry, not less than or equal to, greater than or equal to. The stiffness, minimum stiffness should be a star for the beam. So based upon these relationships, we can derive any formula. First we write I. Let's say we assume it is a rectangular cross section. Since the shape is fixed, let's also write this rectangular cross section. I is equal to, in this case, BH cube over 12. However, area is equal to B times H. Okay, so in that case, we can rewrite the I as A times H square over 12. Okay. Anything else we can replace? We have to see here. Let's see if it is a rectangular cross section. Most probably we will not be able to work with this relationship. Okay. If it is a square cross section, we can directly work with it. But let's see if we can convert this into area here. Okay. So the dimension H here we cannot change. we will not be able to change here. So let's try to work with it if possible. Okay. Okay. So our idea here is to replace the area A with stiffness terms and then rewrite the entire problem. Unfortunately, with the H term, we cannot do it. So most probably we have to work with the square cross section instead of a rectangular cross section. We can choose to simplify the problem. We can choose a square cross section. This is one possibility, or circular cross section. To derive the, we need to derive the material indices, and we can derive the material indices only if it is a square or circular cross section. In that case, we can rewrite the entire formula in terms of one parameter, and this will become h raised to the power 4 over 12. And your area simply becomes, in the case of a square cross section, h square. So it becomes simple. So this is one possibility where we can replace now the moment of inertia with the term a square over 12. So now a becomes, we can replace with a in the formula here rather than substitute anywhere else. So now let's see, the stiffness should be a minimum S star value. I'm going to substitute here C times E times A square over L cube should be greater than or equal to S star. Now A can be written as S star L cube over C, some constant C times E, the entire one raised to the power 1 over 2. Okay. So the minimum value of A should be equal to this here. We want to minimize mass. Minimize the mass. M is written as rho. Rho is constant, fixed variable. A is free variable. Sorry, rho is not constant. Rho is a free variable. A is a free variable, and L is a fixed variable. So we can replace one of the free variables, keeping rho constant. A we can replace. So since A should be greater than or equal to, now instead of writing the equal to sign here, we can say M is greater than or equal to rho times S star over C L cube raised to the power 1 over 2 times L. Now we can group the material properties together. Stiffness is not a material property, it is a functional property. So now I can write M greater than or equal to, group all the functional terms, let's say S star over C, we group it together. The geometric terms we can group it together, which will be L raised to the power 3 over 2 plus 1. So it will be L raised to the power 5 over 2. And group the material properties, rho over, so again S star over C, we have to write 1 over 2 here, not to forget that, and rho over square root of E. So for a light stiff beam, this is the material index, and this particular material index value has to be minimized. Again, what are the free variables? Rho and E are free variables. L is fixed. Okay, and S star is specified. What should be the minimum value of stiffness? So we cannot play with it. The constant C is also fixed. We cannot play with it. So these two terms are fixed. The only thing we can play with is this term over here, the square brackets. So that should be your material index. And this value should be minimized, kept as minimum as possible. We can invert it and write it as the material index capital M square root of E over rho, which should be maximized to keep my mass minimum. If this value is minimum, mass will be the minimum here. Okay, so now what is the Ashby chart I have to pick up? I have to pick up the Ashby chart between Young's modulus and rho. Okay, so let's see here if we have the Ashby chart. This is strength. We have Young's modulus versus rho. Now we have to draw these guidelines here. So which is the guideline? How would I know what is the guideline to be chosen? Again, recall that we are using log to base 10 over here on the x-axis, and we are also having a log axis on the y. So all the quantities are logarithm of the value. So this will be log base 10 for rho, and this guy will be log base 10 E. On this graph, we are supposed to draw the guidelines. The guideline is shown to be square root of E over rho. So this particular line, how do I get it? What should be the slope? So how do you draw it? This all you will be provided is an Ashby chart, empty Ashby chart, but we want to check we have drawn them correctly. How do we do that? To do that, we take this material index and take the ratio is equal to constant. Okay, so why do we take this ratio equal to constant? Because we want to draw lines, guidelines. On the lines, the ratio E over rho should be constant. Okay, so this should be obviously constant right on the line. Now take log base 10 on both sides. So you will get 1 by 2 log E minus log rho should be equal to log C. Okay. You can rewrite this entire formula by multiplying by 2 log E. Take the other terms to the other side. We are going to get 2 log rho plus 2 log C. Okay. So this is in the form y is equal to m times x plus c. So we can write in the form of equation of a straight line, some constant c. What is the slope here? 2. So based upon the slope and whatever may be the intercept on the y-axis, we can draw lines on the Ashby chart. So let's open up an Ashby chart here. I will provide all these Ashby charts in paper, especially for your test 1, and you will have to draw them physically. So here I'm going to show it with the software and on how to draw the Ashby's chart. Draw on the Ashby's chart. Okay. So first let's draw a chart. Let's choose on the y-axis mechanical property and Young's modulus, and in the x-axis a general property which is density. We can see we want it on the logarithmic scale, and the limits are auto set for both x-axis and y-axis. They are on logarithmic scale, not on the linear scale. So this is the diagram I get. When I move my cursor onto a specific bubble, it will show what kind of material it is. In your exam papers, I will literally print out these what these bubbles are. I will be literally printing it out in this way by just clicking on it, and it will show me what kind of material these are. Okay, now if you see the x-axis, log to base 10. Okay, so you can see around some divisions, 1, 2, 3, 4, 5, 6, 7 divisions are shown here. And perhaps you could have got more divisions if you specified what are the limits properly. Okay, so here we have seven divisions. Let's see, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10 divisions. Probably I don't see here. There are 10 divisions in each part. Okay, so we have on the log scale the density provided over here. Let's see if I can make the scale bigger. Unfortunately, I don't think I can make it. Can you guys see the numbers here? 10 and 100, 1000. Are you guys able to see the numbers?
Yes, Diksha.
Okay. So on the x-axis we have on the log scale. On the y-axis we have Young's modulus on the log scale. Now, if you look carefully here, there are 10 divisions. 1, 2, starting from 0. 1, 2, 3, 4, 5, 6, 7, 8. I think 8 divisions are here. Let's test here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So between 10 and 100, there are 10 divisions. Again, between 100 and 1000, there are 10 divisions again. Okay, but this is on a log scale. So we can think if this is the log of the density is equal to 10 here, then at this point here it is 20, 30, 40, 50, 60, 70, 80, 90, 100. Between 100 and 1000 again there are 10 divisions, but they are scaled in logarithmic scale. So the first division here will be 200, 300, 400, 500, 600 like that. So the divisions change between the limits here. So here it is 1000, 2000, 3000 up till 10,000 and so on. Okay, so we need to know what these divisions mean to draw our the guidelines. Okay, so let's see here. Between these two, again we have 10 divisions. So if this is 1 into 10 power minus 4, this will be 2 into 10 power minus 4, 3, 4 like that. And finally 10 into 10 power minus 4 is 10 power minus 3. So between these two divisions, again we have log of E value given in gigapascal. Okay, so this is 0.001 gigapascal, the value here. Okay, here it is 0.01 gigapascal, etc. Now between these again we have 10 divisions. So the first division will be 0.002, 0.003 up till 0.01. In the same way, for each division we can get the values. Okay. So now let's go to the equation here. We have on the y, okay, on the y scale, if I move one division, it will be equivalent to moving two divisions on the density scale. So in other words, if I want to move up where where the ratios square root of E over rho is constant, if I want to move up, then I have to draw lines in such a way that if I move one division above in Y, I have to move 2 divisions in row. So that gives us the idea on how to draw the lines. You can pick any point, for example, 10,000 here. Okay, and I want to draw a guideline from the 10,000 point over here. So how would I draw that? I choose 10,000. In the row axis, I move 2 divisions, 1, 2. So if I move 2 divisions on the row axis, on the x-axis, y-axis, I will move 1 division. Okay, so let's try a simpler point here. So let's try 100. I will choose the point over here, right over here, because we have 2 intersection points. I move 2 divisions, major divisions. If I move 2 divisions here, I have to move 1 division over here. So I can join the point 100 over here and this point over here and then draw a line. So let's check it if the slope comes out to be right. Okay. So we want to maximize the index or yes, we want to maximize the material index. What is the slope? We want 2. So according to this, we will have the slope 2. So log E is this guy and x-axis is 2. So the slope is 2. Now draw it here. Let me pick the point here. Let's see here, it comes out right. So it shows here, sorry, 1, 2 on the y-axis. Okay, sorry. Again, I was wrong here. So if I move on the x-axis 2 units, on the y-axis it will be 2 times 2, which is equal to 4. Sorry for that. Again, you can see if I move 2 units on the x-axis, on the y-axis we can see 4 units. 1, 2, 3, 4. Okay, so I said the opposite way. I should have rather said if I move 1 unit here, 2 units here. So this is the point of intersection. Okay, so we can see from the equation over here, if I take x is equal to 1 unit, our x is equal to log of rho here, and y is equal to log of e. So if I put x is equal to 1, I'm going to get my y as, based upon the slope, 2 times 1 plus c. So every unit, assuming c is 0, we can get rid of this term. We can clearly see if I move in x-axis 1 unit, in y-axis I will move 2 units up. So this is how we draw the line. We can choose each point here and then we can draw the line. Okay. So let's see here again. If we choose this point, again we will see here from this point, if I move 1 unit here, it has to pass through this point over here. Again the slope is 2. Go to this point and we can draw. So when you physically draw them, in x-axis if you move 1 unit, in the y-axis you have to move 2 units up, and then you can draw these lines. Okay. Okay. So now we also need to find what is the value of square root of E over rho over each line. So is it increasing up or increasing down? Do I have to physically figure out what is square root of E over rho for each of this line? That is not necessary. We need not find what are the values. Rather, we can find the general direction along which the value of the material index is maximized. You need not find what are the values here. Okay, so we need to find where this index is maximized, in which direction this ratio is maximized. This is very easy to find. If I choose, since we have these guidelines in this direction, I have to move perpendicular in the perpendicular direction to choose the materials, either up over here in this direction, or I should move down over here in this direction. Okay, so if I choose, for example, to move in this direction, what happens? I have the density, value of density increasing in this direction. However, the value of E is decreasing. So obviously, if density increases and E value decreases, we are minimizing. Yeah. So I do not want to go in this direction. Rather, to select my materials, I have to go 45 degrees towards the higher values of E. Okay, so all my material has to be selected in this particular direction. Now you can have limits for the particular materials which you are about to select, and the limits will be based upon the available materials for the guidelines. For example, I can draw another line here. Again, the slope is 2. Draw another line here, and we can see I can draw several lines. Maybe I can also draw over here. Okay, so when I draw a line over here, if I want a material above the ratio square root of E over rho here, if I select this line, then obviously I do not have any material which satisfies this criteria. So my selection of the limit of the line should be based upon available materials. So I can move around this line slightly here to at least make it possible so that I can select some materials for this particular beam case. So here, if I see here all these bubbles, what I see here is some composite materials, maybe some ceramic materials. Obviously, for a beam, a composite and a ceramic material will not work. Okay, it's not going to work for your application. Most probably, I should go for some kind of ductile alloy. Okay, so from the application, since it is a beam, it should be a ductile alloy or maybe a concrete. Okay, so I can see from all these bubbles what kind of materials are available, plywood, this and that, etc. And based upon this, I can see that I should lower my guideline a little bit to enable more selection of metals and alloys. So here we have concrete, we have brick over here, again composites. These are all ceramics. Obviously, we are not going to select any ceramics. On the high end, we have titanium alloys, okay, very high Young's modulus value. Okay, so now here we have to use another criteria to zero in on the selection. So how can I put another criteria? I can have a certain minimum value of Young's modulus that is required for the beam. So what should be the minimum value of Young's modulus? Maybe I can choose, since this is in gigapascal, for a steel material like steel, we know that it is around I think around the value of the Young's modulus may be around 100 gigapascals or maybe slightly lesser. We can choose a limiting value here. So we will draw also a horizontal line over here to select the material. So in that case, let's see if I draw with a 0 line here, 0 slope. Okay, so you can see a horizontal line. Now in this area, I will be able to select whatever materials I want. So this is how you have to justify. Depending upon the application, you choose appropriate materials. So for a beam, maybe you choose concrete reinforced with steel rods. You can use here again cement, cast magnesium alloys. Maybe you also have some kind of non-ferrous alloys and ferrous alloys. So you have to make sure you include some of the ferrous alloys as well while selecting the materials. So you can move around these guidelines, and based upon that you can have a wider selection of materials. Okay, is this clear on how to draw these guidelines?
Doctor,
Is
in
it
the
clear, guys?
exam, the Young's modulus, the minimum value will be given.
It might be given. Okay, so in some cases, if I do not provide it, you have to logically go by that. Okay, you have to choose through by thinking through it. For example, the typical value of Young's modulus of steel can be used as a reference point to select the minimum value of Young's modulus. There is no absolutely correct answer for these kind of problems. Do you understand that? So there is no specific value of E for which selection of materials can be made. In a design process, it is an open process. So you have to give your reasons why you selected materials with a certain value of E. Is it okay?
Okay.
So in this problem again, what did we do? Here we have a specific stiffness value being given. If you want to have some limit on the stiffness, then the E value here, according to the formula, you can see the E value also has to be appropriately chosen. You cannot have very low E values for your application on beams because you do not want too much of deflection as well, right? So based upon that, you can give a reason, any reason. For example, you can pick a particular application in structures. In building structures, you do not want too much of deflection, and therefore you are choosing a value E equal to this as the minimum value of E for your application. So you can give a reason. Okay, you can choose a particular application and do that. In some other applications, for example, maybe you are using cantilever beam, let's say inside some kind of a sensor. If you use, in the case of sensors, maybe the E value, the limit of E values can change. You have to see a typical application for sensors, and based upon the typical application, what are the E values usually chosen for the sensor. If you are aware of that, then you can choose the typical E value, minimum value to be those values. So depending upon the application, it can change your material indices, the limits of the values of material properties all will change. Okay. So there is no right or wrong answer to these problems. The only right answer is the form of the material index, but rest of it is all based upon the application. You have to come up with some reasons to select the material. Okay. Okay, so let's see. You want to solve more examples for this case? Okay. Can one of you derive what is the material index in terms of, instead of stiffness, if you are given light strong beam, how would you derive the material index in this case? Can one of you derive it? Anybody? Where will I start? Can you please give me some guide on how to start for a light strong beam?
Maybe Hooke's law.
Okay, yes, Hooke's law. But what are the steps I went through to derive light stiff beam? What is the first step?
The objective, minimizing
Objective,
mass.
right? So objective function. Since I have given light beam, so obviously objective function is rho times A times L. So the first step is objective function. Second step,
Fixed variables.
we need to identify fixed variables. What are the fixed variables?
The length and the shape
Right,
of a
usually,
cross section.
right. If you take any structure, the length of the beam is already fixed. Okay, shape of the cross section. So this time let's fix the cross section as a circular cross section. If you take a rectangular cross section, it is a problem. We do not want to solve with a rectangular cross section, square or circular cross section. This will be easier to deal with. Then third step,
Free variables.
free variables. Then what are the free variables?
The density and the
Not the E value here. What are we looking for here? Since it is, we are talking about strength, most
yield
probably
strength.
ductile yield strength. For ductile materials, it's going to be yield strength. Okay, then what other free variables are there?
Area of cross section.
Area of cross section. Okay, so these are the relevant ones. Okay, so the relationship which we should look for, as you said, is the Hooke's law, right?
Yes.
Hooke's law. We write sigma is equal to E times epsilon. Okay, but from here, where do we go? Since we want a strong material, what does it mean?
We can change the strength to deflection over the original length.
Strength to deflection.
No, the strain, doctor.
Strain. Okay, strain. Okay, yes. So based upon strain, what we can say? But first of all, we have to, in the relationship, we have to express in the form less than or equal to, greater than or equal to. So what is this we are looking for here? A
The stress
strong
is less
beam,
than the yield strength.
of course it is less, but we want a minimum value of yield strength, right? So of course, your stress is always going to be less than or equal to yield strength, but this yield strength must have a certain minimum value, right? So For a strong beam, I want to have a limit on the yield strength. Just like for a stiff beam, I have a certain value for stiffness, minimum value for stiffness. In the same way, my yield strength should have a certain minimum value. Okay, so from here, how do I go on? You said strain should be written as change in length over original length. Okay, from here, what do I do? Okay, so we can see most probably E will not occur here. So this is not the relationship I want to have here. Rather, we are bothered about the stresses here. So most probably this is the relationship I am looking for. Okay, so what is stress? Stress is equal to force over area. Whatever force I am going to apply, right, on the beam. In the case of a beam, how do I express the stress? It is a bending moment load. So here I have to write M over I times the maximum stress, right? So here rather we should write it as the maximum stress, M by I o times some C, depending upon the cross section. Here we have assumed a circular cross section. So you need to think through this on what kind of formulas to use. For a beam stresses, this is the formula. For a circular cross section, what is I? What is the formula for I? Pi over 64 diameter power 4. Okay, and C is going to be D over 2. So based upon this formula, we can write for a, since I've assumed it is a beam, I can also express, I'm going to also assume it is a cantilever beam. So I can also express my bending moment in the form of force times length maximum. If it is an end loaded cantilever beam, I can write the maximum bending moment is going to be F times L. Okay, so for this, these conditions are now I can derive what is the maximum stress. Maximum stress is going to be FL over, I can write C over I as I over C in the denominator. If I divide these two quantities, I'm going to get here pi over 32 d cube. Okay, but before I do that, I have to express the area. I forgot about that. So let me clear here and then express the I values properly. Okay, this implies I can take the ratio I over C is equal to pi over 32 d cube. However, the area of cross section A is equal to pi over 4 d square. Okay, in other words, d can be expressed here by taking the other terms to the other side, 4a over pi square root. Take this d, substitute over here, and get I over C. The section modulus Z equal to I over C becomes pi over 32, and we have here If you take a look at it, d cube, so we want to know what is d cube here. If you take cube of this entire value, I will get 4a over pi times square root of 4a over pi. Okay, so I can write times square root of 4a over pi. We can cancel the pi's off, and your z will become, here we have 4, inside the square root we have another 4. We can take the square root of 4 as 2. 2 times 4 is 8. 8 over 32 will become 1 over 4. So we have a over 4 outside. The denominator we have square root of pi, and here we can see a times root a will become 1 plus 1 over 2 will become 3 over 2. Okay, so finally this is the form we have. Okay, so a 3 over 2. So now this is nothing but m over z can be written FL over, in terms of area of cross section, a raised to the power 3 over 2 4 root pi. I can take it to the numerator. Now the sigma max has to be, of course, less than the minimum strength of the material, Sy star. Now we can rewrite the entire equation here. Take a to the other side, which means obviously a should be greater than or equal to. When I take a to the other side, I will get FL 4 root pi FL over Sy star, and we can clearly see here I have to take raised to the power, since I have a raised to the power 3 over 2, I'm going to raise it to the power 2 over 3 on both sides, and then I will get this relationship for a. Now I can rewrite the mass equation. M is equal to rho times area. Okay, so instead of writing equal to, since a should be greater than or equal to that, here also your mass should be becomes greater than or equal to 4 root pi FL Sy star or 3 into length L. We can group the terms together. The functional properties, F is a force here, so it is a functional property. We can group it together here. 4 root pi F, and I'm going to write it as 2 over 3 multiplied by the geometric property. To think of the geometric property is the length L. L raised to the power 2 over 3 times L. So we have to have here plus 2 over 3 plus 1. It will be 5 over 3. And then the material properties together. Rho over Sy star raised to the power 2 over 3. Okay, so which means that to minimize mass, I have to keep this ratio minimum for the beam. And usually the material index is taken in the opposite inverse way. So material index should be equal to 2 over 3 here over rho. So this is our material index. So long strong beam. So this is the material index, which means I have to choose appropriate Ashby chart here. So here we are going to choose with the mechanical properties and the yield strength of the material in a logarithmic scale. And we do the same thing for x-axis density on the logarithmic scale. We get another chart over here. Let's see here. Since we have probably drawn these lines here, it has grayed out in the other chart as well. Now after removing that, you can see the complete chart. Okay, so again yield strength. So to draw the guidelines, what do? Again we take log here, but before taking log both sides, we want this ratio to be constant on the guideline. So this is some constant C. Take log base 10 both sides and we get yield strength 2/3 is equal to log rho plus log C. You can take multiply by 3/2 all throughout. Since this is some constant, I'm even though I multiply 3/2 log C here, I can write. Okay, so I'm going to leave it as such. This is some constant, whatever is the constant. So now this is in the form of y is equal to m x, right? So this value will be equal to m plus c. This entire term is equal to c, some constant. So the slope is 3/2. So if I move one division on the x here, I will have to move 3/2 divisions, 1.5 for the y-axis. So you can draw based upon this. So if I move one division on the x-axis, let's say from this point, I have to move 1.5 divisions here. So 0.1, 0.2, 3, 4, 5. So around somewhere in between here. Okay. So let's say if we start over here, should be somewhere here. The intersection point should be here. So let's draw the line and the slope value is 3/2, which is 1.5. Okay. Then let's choose this point and you will see it passes approximately 0.5, 1.5 over here. Okay, so let's see. No, it's actually moving exactly 1/2 of the value here. So yes, so it should be, because taking into account this entire value is x, it should be 1.5 times x. So exactly half of the distance between these two lines. Okay. So if I choose another point, let's say over here, it will move exactly halfway in between here.
Victor, you can go 3 in y direction and 2 in x. It will be better.
That's also right. Because if you cannot exactly figure out what is halfway here, then that's also right. So here you can see if I move 2 divisions here, it will be 3 divisions, 1, 2, 3, exactly 3 divisions over here. That's also right. So let's start here, maybe here. This is better because we will have more choice of materials over here. So again, we can see the line. So of course there should be a minimum value of the strength. The strength of steel is usually in terms of megapascals, and the strength is also provided in megapascal here. Again, this is on logarithmic scale. Remember, this is 0.1 megapascal, 1, 10. And if you actually think about it, the steel material has around 200 megapascal. So maybe this is the point here. So we can have a limit of the strength as 100 megapascal. Let's see. Also, aluminum has 70 megapascal. If you want to include that, maybe you do not want to go that high. So 10, 20, 30, 40, 50, maybe at 60, you have the minimum value. So now we can draw another guideline with a zero slope, maximizing the index 10, 20, 30, 40, 50, and 60. If I draw here, it will draw the horizontal line and we can select materials in between here. If you point to any bubble, you can see different alloys being displayed here. Okay. So this is how you select. Again, in which remember that we want to maximize this guy. In which direction it is maximized? Very easy, very simple here. Looking at the direction of the guidelines, we have to move perpendicularly up or down. If you move down, obviously the ratio is minimized because density has higher values and yield strength has lower values. You need to go up in this direction to maximize the quantity, and therefore these are the materials to be selected. Okay, so let us see if some ferrous alloys are listed here. I cannot see any ferrous alloys here. Copper, this is zinc. Usually it is a very small bubble. Ferrous alloys, we have cast iron here, low carbon steel. Okay, so this is the, usually we select low carbon steel material with high ductility. We also have other alloys, maybe tungsten alloy. This is silver, obviously we do not want to use. There should be also titanium alloys if you go for high strength materials. Not sure where it is here. So we have the titanium alloy. We can clearly see the yield strength is around 1. We have in this particular case 1 gigapascal. Okay. Now this particular chart does not give you the list of all the materials. Sometimes we will need a much more detailed analysis specifically for materials. In that case, we need to go and select. Let's see here. Let me start a new project. Save. No, I don't want to save. Okay, again, we don't have. Sorry. This is not the one. Go back to home. We want to change the level. I want to go to level 3, and that's what I'm seeing here. Specifically, I don't have that. Change database. Okay. So if I go to level 3, I will have much more details on the charts. So let's see again, chart. You can see specific materials are being listed here with the standards. The identification of the material is through the standards here. Some of the materials, at least. Let's draw the same Ashby chart. Go to mechanical properties, Notting's modulus, yield strength. And on the x-axis, we go for general properties, physical properties, and density, and draw. Here you can see great detail on what the different materials are. Okay, so much more detailed here. So to use these kinds of chart, we definitely need a software, otherwise it will be impossible to use them. But still we can draw the guidelines and see on the left hand side pane over here what are the different materials those are available. And let's say 1.5 here, and we want to maximize the index. Draw the same guidelines. Maybe somewhere here, and we can see whole range of materials, aluminum alloys. These are some kind of I think let's see here. These are composites, most probably. There are foams and different kinds of materials here. Again, we have aluminum alloys, whole list of aluminum alloys here. We have a huge list of materials. So these are all non-ferrous. Then we have carbon steel, again with ASI identification for each of the materials. Okay, you can see whole list of materials given here. Okay, unfortunately, we do not have the software freely available, and I cannot provide you in your exam an Ashby chart like this, much more detailed Ashby chart, because too many bubbles are there, and I cannot list each and every material here. Okay. Any questions on material index here?
Doctor, can you in the exam talk about other factors that maybe affect material choice, like cost and other
Okay.
factors?
I'm not going to ask you these things explicitly because you do not have the data in the exam. Unless I give you the data, it is not possible to do that. So I'm not going to ask regarding cost and other phenomena here. Rather, what makes common sense. For example, if I ask you to choose a material for lens, okay, in Hubble Space Telescope or some other kind of telescopes, we use lens. And if you are asked to figure out for lens what is the material index, I will give you some equations and maybe you come up with the material index, let us say some kind of material index. What kind of material are going to choose for lens? Obviously, you have to choose a material that is transparent. You cannot choose any metal here, right? The material has to be transparent, and mostly these will be glasses and other types of ceramic materials, ceramics mostly, right? Only these kind of materials, they are transparent. So these are common sense here. So I can ask you questions like this, and you will have to give a reason, and the reason will involve lens should be made out of transparent material, and therefore we have to concentrate within a particular class of material, which are glasses. However, the lens should also not undergo too much deflection, right? There are other conditions. So I can give you deflection equations, and I may mention a stiffness for the lens. Okay, so based upon the stiffness, E versus rho properties, you have to choose from the Ashby chart specific materials. And one of the reasons will also include it has to be a transparent material. So I concentrate within a specific class of materials which are called as glasses in the Ashby chart. I cannot choose each and every material. These are common sense reasoning. So this is what I am seeing or expecting in your answers. Is it clear?
Yes.
So cost and other data, unless I provide you a table. table
Like in
for
the
choice.
assignment, Doctor, the assignment was diamond with the options. Obviously, diamond cannot be used for table legs.
Yes, that is okay. That is common sense, right? Obviously, we cannot go for silver, for gold or diamond. For some applications, yes, we cannot go for that. In some applications, maybe diamond will work. For example, cutting tools, right? What are cutting tools? Tools that cut other materials. So in these cases, diamond tipped tools may work. In other cases, maybe it is too expensive. Depends upon the application. So if I ask you to select a material that can cut diamonds, what is the material that can cut diamonds? Obviously, you have to choose a material. What is the material?
Only diamond.
Yes, obviously it has to be diamond, but it is going to be too expensive. So what do we do? Artificial diamonds. Okay, there are also artificial diamonds which are done. Besides that, we know ceramics have very high strength, very high hardness. So we can choose high hardness materials. Although it is not as hard as diamond, still we will be able to use some of the ceramics. Although it will get destroyed in the process, still we can use these materials for polishing diamonds, right? How do we polish diamonds? By using other ceramics, and we can polish them. So, or artificial diamonds. So you can use common sense arguments. Your artificial diamonds are not expensive, so we can use here. So this is what I expect. When I say some of the reasons, you have to come up with reasons here. Some of the reasons. You can come up with other reasons. There is no right or wrong. Of course, there is a wrong answer, but there is no specific right answer. There may be multiple solutions here. So these are open problems, and I just want to see what are the reasons you use for selecting materials. Okay. Okay. Of course, if you know generally that the cost of the material is very high, then you can specifically state that. Okay, so this is with respect to material index. We are done here. We can also go through other problems, other type of problems, example problems we may get. Specifically go through problems, what is given in the assignment. Okay, so in the assignment, what kind of problems I gave? Maybe beams subjected to some kind of forces. Beams could be subject to forces distributed or concentrated, moments distributed or concentrated, and then are a combination of moments, torques, and forces. And then you have to come up with the stress tensor with all the 6 independent components. Once you come up with these stress tensors, you will have to find principal stresses and apply failure theories. So this is the kind of problem you will get. Definitely you will get. And specifically we are talking about static failure theories. Okay. So in chapter 3 and chapter on failure theory, the problem will be combined problem. You might get one combined problem where you have all the combined forces, and you will have to come up with a 3D stress, principal stresses, and apply the failure theory and find a particular dimension of the component or design that component. Okay, or maybe you calculate the factor of safety and tell us whether it is going to fail or not fail. Now, besides this, you will definitely get a problem on material index, a problem like this, and definitely multiple choice questions on chapter 1 and 2. 1 and 2 multiple choice MCQs on theory. So for example, I can ask what kind of materials have DBTT? What is DBTT? Anybody?
Transition from ductile to brittle temperature.
Right, ductile to brittle transition temperature. What kind of materials have DBTT and what materials do not have
BCC
DBTT?
metals.
Right, BCC alloys always have this. FCC do not have this. Okay, so similar questions could be asked for other properties as well. So I can ask you what kind of tests are done for impact conditions, what kind of tests are done for let's say quasi-static loading. I can ask you, for example, what is Luder's band? These things I went through in your second chapter, Luder's band. So you can write it clearly. Okay. Then what other things I can remember about? Remember the difference between ductile, brittle materials, what make them ductile or brittle, what is slip, what is dislocation. Okay, if you take a ductile material, apply a twisting torque, what will be the orientation of the crack formed when it is twisted up till failure? Or if you take a brittle material and apply a twisting torque, how will it break? Okay, so you have to know these things. Ductile, brittle materials, then stress concentration factor, KT, KTS, how do we use them for ductile or brittle materials? Okay, then what else we have? So these are some of the things you should be aware of while talking about the material properties. In the first chapter, I can ask you about conceptual design phase. We have the right after the conceptual design, what is the phase we have? The embodiment design phase, and then detailed design. You should know what are these different design phases. Important also for the material properties, I forgot about it. Numbering systems. What do they mean for steel and aluminum? Steel, aluminum. Okay, UNS numbering system in particular. Okay, so I can ask you, for example, what is 4340 steel? I will give you a table. From the table, you should be able to explain what is 4340 steel, for example. Okay, then the chapter 1, what else we have? Chapter 1 mainly only this part, conceptual design phase, and Most of the other parts are general theories which I will not expect you to remember. So these are the things I can ask you questions in. Okay. Any other question?
The exam will be 2 hours, Doctor.
Yeah, I will give 2 hours. But I don't think you will require 2 hours. Maybe 1.5 hours you can finish the exam and leave. In 1.5 hours you should be able to finish it. Your multiple choice questions, about 5 to 10 questions, which you should be able to finish in about 10 minutes. Your material index question, I will give you all the formulas which are required. For example, in the case of the light strong beam, maybe I will give you this formula, m over z, and then you will have to come up with an idea to substitute for the area A. Maybe this one takes about half an hour, let's say. And another problem on the, not on the material index, specifically with combined forces, applying the failure theory, etc. will, let's say you take 45 minutes. So about 1.5 hours, you should be able to finish the exam. So three types of questions, multiple MCQs, maybe 5 to 10 questions, one problem of this type with static failure theory, and one problem on material index. Should not be very heavy, and you should be able to finish in 1.5 hours. Is it clear?
Yes, clear, Doctor.
Yeah. Okay, so please go through it. I have given you in very detail what to expect in the exam. Don't be surprised during the exam. The exam is usually very, very easy for design course. There are only certain 2 or 3 types of problems that can appear in your exam and nothing outside of that. The procedure is the same. All the formulas will be given in the formula sheet, and you will just have to follow the steps. If you follow all these steps, it is very easy to score 100% in the exam. Okay, so good luck with you guys, and I will meet you after the break. If we have any class after the break and before the exam, I will start with the new chapter. Otherwise, we will meet during the test here, not the exam, during the test. Okay, again, on April 7th, between 2 to 4, you have your test. I'm going to post the information. During your break, I will also post a quiz, take-home quiz, in the same model as the test, so that you will have an idea. Please do not copy. Work it on your own and try to solve the problems. If you solve the problems on your own, you will be able to do your test as well. Okay. So see you guys, and I will meet you after the break. Have a nice break. Okay. See you guys.
Thank you, Doctor.
Welcome.